All right, so we said the mean value theorem was of great theoretical importance. So that means we want to use the mean value theorem to prove some other things, right? So that's, in this section, this is where you will write some basic proofs down. So you'll make a sound mathematical argument. So here's an example of that. Grand Forks is 70 miles from Fargo, and the speed limit on I-29 is 80 miles per hour. So let's just assume that our travel is restricted from one of the Fargo exits to one of the Grand Forks exits. So if I make it to Grand Forks from Fargo in 50 minutes, then at some point in my journey, I definitely broke the law. How can we prove that? So if you're the lawyer and you want to prove that I'm speeding, or you're the police officer and you want to prove that I'm speeding, how are you going to do that? Well, this is where the mean value theorem comes in. So we want to prove that at some point my velocity was greater than 80 miles per hour. So let's write down a proof of that. All right, so here's how we're going to do this. Again, we're just going to restrict ourselves to the I-29 portion of the travel. So, we're not stopping or making any turns, right? It's a straight shot. So therefore, the distance then is steadily, right, increasing, or, right, it's not gonna increase and then decrease. So there won't be any sharp turns or anything like that. So let me let d of t be the distance from Fargo function. So, right, d of t is just some function that when I plug in a particular time, it returns the distance that I am from Fargo in my car. Okay. So then d is continuous on that time interval. So remember, we made it from Fargo to Grand Forks in 50 minutes. Let me change that to hours, because we want to do this in terms of miles per hour, right? So the time interval is from 0 to 50 over 60 hours, right? So d is continuous on this interval, and it's differentiable on this interval, on the open interval, because we're not stopping or turning or no sharp turns or any of that. So the MVT, the mean value theorem, says there's some number c in my time interval. So from the starting point to the 5/6 of an hour, such that d prime of c is equal to the average rate of change, right? So the instantaneous rate of change is equal to the average rate of change. But what is d of 50 over 60? In other words, where am I 50 minutes from the start of my journey? Well, I'm in Grand Forks 50 minutes from the start of the journey. And so how far is Grand Forks from Fargo? Well, it's 70 miles, right? So when at the end of my journey, I am 70 miles away from Fargo. At the beginning of my journey, I am 0 miles away from Fargo. And so to divide by 50 over 60 minus 0, that's just to divide by 5 over 6. So you work this out and you get 84. So that says the derivative of my distance function at the point C is 84. In other words, my velocity at the point C, my instantaneous velocity, because it only takes an instant to break the law, d prime of c, my velocity then, is 84 miles per hour. That's bigger than 80, and so I definitely broke the law at t equals c hours or minutes or whatever you want. Okay. All right, so this will be our last video lecture on the mean value theorem, and we want to prove something that will come up later on in the course. So we want to prove that if the derivative of a function is equal to 0 everywhere, then the function must be constant. I think our intuition is okay with this, right? Because if the derivative is 0 everywhere, then that means the slope of the curve is 0 everywhere. And the only way that can happen is if you've got a horizontal line, right? That's the only type of function that's got 0 slope everywhere. But we want to prove this carefully, right? We want to prove this without drawing a picture and writing pages and pages of an argument. We want to keep it short and sweet, right? So here's how you would prove this. I'm going to pick any A different from B in this domain D, so in some set of numbers. And I'm going to show you that f of A must be equal to f of B. So here's what that says. Pick any two arbitrary points in the domain D, right? When I plug them into F, they've got to have the same value. So pick, right, if you keep picking 2 points at a time from D, they will always have the same value. In particular, if one is fixed and you pick a bunch of other ones, they will all have the same height as the one first point that you picked, right? So everything's going to have the same height in this case. So that's how you would show something is constant, right? So again, pick any A different from B, or A different from B in the domain D. So we know that F prime is equal to 0 for all X in D. In other words, F is differentiable everywhere in D, right? And so that means it's differentiable on the closed bounded interval. I mean, I guess we should assume that D is an interval. That would be helpful because we want to make sure that this thing is actually contained in D. So F is differentiable everywhere on D, and so it's differentiable everywhere on A to B. And it's continuous then everywhere on A to B. So the mean value theorem applies to F. So there is some number C in the interval from A to B such that F prime of C is equal to F of B minus F of A over B minus A. But what is F prime of C? We know it's 0, right? So I know that 0 is equal to this fraction. Well, the only way that a fraction is 0 is if the numerator is 0. And the only way that F of B minus F of A is equal to 0 is if F of B is equal to F of A. So any 2 points that I pick in the domain, their images will have the same height, no matter which ones I pick. So that shows that the function is indeed constant everywhere on the domain D. Okay, here's an example using the thing that we just proved, that if a function is constant if a function has derivative 0 everywhere, then that function must be constant. Okay, so let's use that fact to prove this identity. We want to show that the inverse tangent of x plus the inverse cotangent of x is equal to pi over 2, right, for all x. So no matter what x I plug in, I'm going to get pi over 2. That's similar to like the identity sine squared of x plus cosine squared of x is equal to 1. In fact, this same method of proof will work to prove that fact if you didn't already believe it. Anyway, so let me just let g of x be the thing on the left-hand side. So tan inverse plus cotan inverse. And now take the derivative. I know the derivative of tangent inverse of x is 1 over 1 plus x squared. And I know the derivative of cotangent inverse is negative 1 over 1 plus x squared. And so the derivative then of g is just equal to 0. Well, the previous theorem says that this function then must be constant, right? So I know g of x is equal to c for every real number x, right? So now what is this constant going to be exactly? Well, it's this constant c no matter what x I plug in. So once I plug in one number, let's plug in a convenient number like 1. When I plug a 1 in for this thing, I get pi over 4 plus pi over 4, so I get pi over 2. So I know that g of 1 is pi over 2, right? But g of x then is equal to c no matter what the x is. So in particular, g of 1 is equal to c. But g of 1 is equal to pi over 2. Therefore, c must be equal to pi over 2. So g of x is equal to pi over 2, and we're done, right? And that'll prove the thing that we were trying to prove.